Every single galaxy is connected by an invisible cosmic architecture. This is the Great Cosmic Web, the largest structure in the universe, a hidden network of dark matter and gas that binds the cosmos into a single, interconnected whole. By the end of this, you will understand the fundamental forces that shaped this grand design and forever change how you picture the night sky. We will uncover how astronomers discovered these ghostly filaments and what strange, cosmic rivers of galaxies can tell us about our own place in the universe. What does it feel like to know we are part of something so vast and intricately woven together for centuries? The universe appeared as a collection of solitary islands. Astronomers, armed with increasingly powerful telescopes, charted these galaxies as isolated beacons of light, adrift in an unimaginably vast and silent ocean of blackness. Even the monumental discovery by Edwin Hubble that the universe itself was expanding did little to change this fundamental feeling of cosmic loneliness. The grand narrative was one of separation, with these stellar cities separated by voids so immense they seemed utterly devoid of meaning or substance. This was the accepted reality, a universe where the emptiness between galaxies was just that, empty, a void that served only to highlight the isolation of each island universe. Yet this picture was deeply puzzling. If the cosmos was truly just a random scattering of galaxies in a void, why did their motions and arrangements suggest an unseen hand at work? The very emptiness that seemed so simple was in fact the biggest clue that we were missing something profound. The stage was set for a revolution, one that would replace this vision of lonely islands with the discovery of a hidden continent, connecting every galaxy into a single, breathtaking structure. The galaxies were not drifting aimlessly. Their motions held a secret, a subtle deviation from the expected flow of cosmic expansion that astronomers called peculiar velocities. It was as if every galaxy was not only riding the tide of the expanding universe but also being tugged by invisible strings. This was the first tangible clue that the emptiness of space was an illusion. In the 1970s and 80s, a monumental project began to map this hidden activity. The CFA Redshift survey started meticulously plotting the positions and speeds of thousands of galaxies. What they found was astonishing. Instead of a random scattering, they discovered entire rivers of galaxies, all flowing in concert toward immense, unseen concentrations of mass. These were not small currents, but vast flows spanning hundreds of millions of light-years. Entire clusters of galaxies were moving together, pulled by gravitational forces so powerful they could only be explained by the existence of structures far larger and more massive than anyone had dreamed. The emptiness between galaxies was not empty at all. It was filled with an invisible architecture, a cosmic framework whose gravity was orchestrating the motion of every galaxy we could see. This was the foundation, the first direct evidence that our universe is woven together into a single, coherent structure. This cosmic tug-of-war pointed to an architect, a hidden builder whose gravity was sketching the blueprint for the entire universe. That architect is dark matter. You cannot see it, you cannot touch it, and it does not emit or reflect any light whatsoever. Yet this invisible substance is the fundamental reason the cosmic web exists at all. Its presence is felt only through its immense gravitational pull, a ghostly hand that sculpts the cosmos on the grandest scales. Think of it like the steel framework of an unimaginably vast skyscraper, completely hidden behind the walls, but without which the entire structure would collapse into chaos. Dark matter forms this exact kind of gravitational skeleton for the universe. In the early cosmos, slight ripples in the density of dark matter began to attract more and more of this mysterious substance, growing into massive, invisible halos. These halos acted as gravitational wells, pulling in the ordinary gas and dust that would eventually ignite into stars and form the galaxies we see. Without dark matter's immense gravitational pull, galaxies would have remained scattered randomly across the void like dust motes in an empty room. There would be no great clusters, no flowing rivers of galaxies, and certainly no web. The distribution of dark matter dictates everything, determining the exact locations where galaxies blossom and the invisible filaments that connect them across billions of light years. To truly understand the cosmic web, we must first unravel the mystery of the invisible architect that designed it. Gravity is the patient artist that took this invisible framework and began to carve the universe we recognize today. It works on a timescale almost impossible to comprehend, transforming the faintest whispers in the early cosmos into the grandest structures imaginable. In the first moments after the Big Bang, the universe was a nearly smooth, hot soup of particles and energy, but it was not perfectly smooth. Tiny, random quantum fluctuations, smaller than a single atom, created minute differences in density. These were the seeds of everything to come. Gravity seized upon these tiny imperfections. Over billions of years, it tirelessly amplified them. Regions with just a little more mass exerted a slightly stronger gravitational pull, drawing in more and more matter from their surroundings. This created a runaway effect, a cosmic feedback loop where the rich got richer and the poor got poorer. The densest regions evolved into the massive nodes of the cosmic web, the great clusters where thousands of galaxies swarm together. The emptiest regions, having lost their matter to the growing nodes, expanded into the vast, dark voids that separate the web's strands. This entire process, known as gravitational instability, is the fundamental mechanism that weaves the cosmic tapestry. We can witness this artistic process not with a telescope, but through the power of supercomputers. Simulations like the famous Millennium simulation start with a virtual universe representing those initial tiny ripples. They then apply the laws of physics with gravity as the lead actor and let the simulation run for billions of virtual years. The result is breathtaking. Before your eyes, a formless cloud of particles organizes itself. It collapses and condenses, first into delicate tendrils, then into a stunningly detailed network of filaments and clusters that looks exactly like the cosmic web we observe. It is a digital proof of gravity's grand design, a confirmation that this single, relentless force is responsible for the architecture of the entire visible universe. Every galaxy, every cluster, every filament is a testament to gravity's slow, patient, and unstoppable work. The blueprint for this entire cosmic structure was drawn in the universe's very first moments. Long before gravity began its patient work, an event of unimaginable power set the stage for everything to come. This event is known as cosmic inflation, a period of explosive expansion that occurred in the first tiny fraction of a second after the Big Bang. During this fleeting instant, the universe did not just grow, it inflated faster than the speed of light, stretching from a subatomic speck to a volume far larger than our entire observable universe today. This incredible growth spurt had a profound effect on the fabric of reality itself. It took the faintest quantum fluctuations, the tiny jitters inherent to the quantum world, and stretched them across the cosmos. Think of a tiny, microscopic wrinkle on the surface of a deflated balloon. As you inflate the balloon to an immense size, that tiny wrinkle becomes a vast, continent-scale feature. Inflation did exactly this to the infant universe. It transformed those subatomic quantum ripples into macroscopic variations in density. the very seeds that gravity would later use to build galaxies and weave the cosmic web. Without this initial stretching, the universe might have remained too smooth and featureless, with gravity having no starting points from which to build. The great cosmic web, with all its intricate filaments and colossal voids, might never have formed at all. We can actually see the imprint of these primordial seeds today. They are frozen in time in the oldest light in the universe, the cosmic microwave background radiation. This faint glow, which fills all of space, is a snapshot of the universe when it was just 380,000 years old. The subtle temperature variations in this ancient light, those hot and cold spots we can map with satellites, are direct images of the density ripples created by inflation. They are the blueprint, the infant picture of the cosmic web, showing us where matter was slightly denser and destined to collapse, and where it was emptier and destined to become a void. This means that the largest structures we see today, spanning billions of light years, owe their origin to quantum fluctuations so small they are almost beyond comprehension. The invisible threads connecting every galaxy were spun from the fabric of spacetime itself in the universe's first fleeting breath. To see this invisible architecture for ourselves, we needed a way to map the unmappable. This monumental task fell to one of astronomy's most powerful tools, the Redshift survey. The concept is beautifully simple in theory, yet its execution has revolutionized our cosmic view. As the universe expands, it stretches the very fabric of space, and in doing so, it also stretches the light traveling through it. This stretching makes the light from distant galaxies appear redder than it actually is, a phenomenon known as redshift. By measuring precisely how red a galaxy's light has become, astronomers can calculate not just its distance from us, but also its velocity within the cosmic flow. It is like listening to a train whistle. As the train moves away from you, the sound waves stretch and the pitch drops. Redshift is the cosmic version of that dropping pitch, a telltale sign of a galaxy receding from us in an expanding universe. Projects like the Sloan Digital Sky Survey took this principle and scaled it up to an almost unimaginable degree. Instead of studying a few hundred galaxies, this ambitious project set out to systematically map the sky, cataloging the positions and redshifts of millions of galaxies. For the first time, we were not just looking at individual points of light, we were assembling a three-dimensional atlas of the cosmos. When you plot all that data, something breathtaking emerges from the noise. The galaxies are not scattered randomly. They coalesce into a delicate, lace-like structure. You can see them clustering along immense, intersecting filaments, like glitter sprinkled along the strands of a vast, invisible spiderweb. Between these brilliant strands lie the cosmic voids, unimaginably vast regions of near-total emptiness that can span hundreds of millions of light years. These three-dimensional maps are the ultimate proof of the cosmic web, a direct observational snapshot of the grand design. This data does more than just confirm the web's existence. It allows scientists to take its measurements. By analyzing the precise distribution of galaxies within the filaments and the staggering scale of the voids, we can test our theories of dark matter and gravity against reality. We can understand how the web has evolved over billions of years and trace the peculiar flows of galaxies as they are funneled along these cosmic highways toward the great clusters. Every new data point from these ongoing surveys is another stitch in our map of the universe, refining the blueprint and revealing a structure of such beauty and complexity that it seems almost impossible to believe it was born from random quantum seeds. This ancient light, the cosmic microwave background, is far more than a simple afterglow. It is the oldest photograph ever taken, a snapshot of the infant universe when it was just 380,000 years old. At that moment, the cosmos had cooled enough for atoms to form, allowing light to travel freely for the first time. That light has been traveling ever since, stretched and cooled by the expanding universe into the faint microwave whisper we detect today. It is a fossil, yes, but a fossil that is still all around us, a background hum of creation that fills every cubic inch of space. The most profound secrets are hidden within its near-perfect uniformity. When we map this radiation with exquisite precision, using instruments like the Planck satellite, we find it is not perfectly smooth. It is mottled with tiny temperature variations, spots that are just millionths of a degree warmer or colder than their surroundings. These minuscule differences are everything. Each slightly warmer spot marks a region of the early universe where matter was a little more densely packed. Each cooler spot signifies a region that was a little more empty. These are the very seeds we have been searching for, the primordial density fluctuations imprinted by inflation. This map is the universe's original blueprint. It shows us the exact distribution of matter and gravity at a time before a single star or galaxy had even formed. The pattern is a cosmic prophecy. The denser patches seen in this ancient light are the precise locations where dark matter would begin to clump, where gravity would work its slow magic, and where, billions of years later, the great filaments and nodes of the cosmic web would eventually condense. By comparing this ancient blueprint to the modern cosmic web mapped by galaxy surveys, cosmologists have found an undeniable match. The large-scale structures we see today align perfectly with the fluctuations predicted by the CMB. This is the crucial evidence that links the theoretical to the observable. It confirms that the entire complex architecture of our universe, with its glittering filaments and desolate voids, grew naturally and inevitably from those initial quantum seeds. The invisible threads connecting every galaxy were not only predicted, they were foreshadowed in the universe's very first light. These cosmic blueprints find their ultimate expression not in a telescope, but inside a supercomputer. The most advanced simulations, like one called Illustris TNG, act as digital time machines. Scientists begin by programming the fundamental laws of physics and seeding a virtual universe with the exact pattern of ripples we see in the cosmic microwave background. They then set this digital cosmos in motion, allowing gravity, dark matter, and gas to interact over billions of simulated years. The result is a breathtaking cinematic unfolding of creation itself. We can watch as a formless cloud of dark matter particles begins to clump and collapse. Ghostly tendrils emerge first, weaving themselves into an intricate lattice. Along these invisible filaments, ordinary matter, the gas that will become galaxies, is funneled like water flowing into riverbeds. It streams toward the intersections, piling up into brilliant nodes that become galaxy clusters. The simulation is not just a pretty animation, it is a rigorous test of our entire cosmological model. When we compare these virtual universes to the real maps from Redshift surveys, the match is astonishing. The simulated cosmic web looks almost identical to the one we observe, with the same filament lengths, the same cluster sizes, and the same vast, empty voids. This powerful agreement confirms that our understanding of the universe's basic ingredients and rules is fundamentally correct. These digital laboratories also let us explore cosmic history in ways no telescope ever could. We can rewind the simulation to see what the web looked like when the universe was only half its current age, or fast forward to witness its future evolution. We can watch galaxies collide and merge as they travel along the cosmic highways, and observe how supermassive black holes at the centers of galaxies inject energy back into the web, shaping its growth. This computational artistry transforms an abstract concept into a dynamic, evolving structure. It brings the invisible architecture of dark matter to vivid life, revealing a universe that is not static, but a living, breathing tapestry, continuously being woven by the relentless force of gravity. These filaments are the true superhighways of the cosmos. They are not just faint tendrils, but dense, structured threads that form the primary connective tissue of the universe, binding the great galaxy clusters together like cities linked by immense, invisible freeways. Picture the very largest of these filaments, stretching for hundreds of millions of light-years across the emptiness. They are colossal rivers of dark matter, their immense gravitational pull acting as the guiding channel for everything that travels within them. Along these dark matter riverbeds, vast reservoirs of hydrogen gas flow steadily and silently. This gas is the lifeblood of the cosmic web, the raw fuel for future generations of stars. As this gaseous material streams along the filament, it is funneled directly toward the waiting galaxy clusters at the intersections. When this river of gas finally pours into a cluster, it can trigger ferocious bursts of star formation, lighting up entire galaxies and fueling the growth of the supermassive black holes that dwell at their hearts. This continuous flow is what keeps the great clusters alive and dynamic, preventing them from simply burning through their fuel and fading away. But what does it feel like to travel along one of these cosmic highways? If you were a galaxy, your journey would be a slow, graceful drift along a gravitational current pulled by the invisible mass of the filament. You would not be alone. You would see other galaxies sailing alongside you, all moving in the same general direction toward the brilliant, crowded node ahead. The space between you would be filled with that thin, streaming gas, a faint intergalactic wind. These filaments are not all identical. Some are thick, prominent bridges connecting two immense superclusters, like the gravitational equivalent of a massive suspension bridge. Others are thinner, more tenuous threads, perhaps connecting a smaller group of galaxies to the main web. Their density and structure tell astronomers a detailed story about the history of the universe. By measuring how galaxies are distributed within a filament, scientists can trace the flow of matter, understand the strength of the gravitational forces at work, and even estimate how much dark matter is woven into its structure. These highways are more than just connections. They are the universe's primary system for distributing its material, ensuring that matter, the building blocks of everything we see, reaches the places where it is needed most. At the end of every cosmic highway lies a brilliant, chaotic metropolis. These are the nodes of the cosmic web, the grand central stations where multiple filaments converge and the density of matter reaches its peak. If the filaments are the freeways, then these nodes are the sprawling galactic cities, home to thousands of individual galaxies all swarming together in a relatively small volume of space. The most famous of these, like the Coma cluster, are staggering in their scale. Imagine a region of space tens of millions of light-years across, so packed with galaxies that a single telescope image reveals thousands of them, from majestic spirals to featureless elliptical giants, all bound together by an unimaginably powerful gravitational field. This gravity comes not just from the galaxies we can see, but from two other, even more dominant sources. The space between the galaxies is filled with a seething ocean of superheated gas, so hot that it glows in X-rays, and it contains more ordinary matter than all the stars in all the galaxies combined. And holding this entire chaotic scene together is the true heavyweight, an immense halo of dark matter whose gravitational pull is the ultimate anchor, preventing this entire cosmic city from flying apart. The activity within a node is relentless. Galaxies, pulled in from the surrounding filaments, constantly interact and merge. These colossal collisions can strip galaxies of their gas, trigger frantic waves of new star birth, and funnel material onto the supermassive black holes at their centers. When this happens, these black holes can ignite as active galactic nuclei, becoming some of the most luminous objects in the universe and blasting powerful jets of energy back out into the surrounding web. A node is not a peaceful place. It is a crucible of constant change, a gravitational powerhouse whose influence stretches far back along the filaments that feed it, dictating the flow of galaxies and gas across billions of light years. It is here, in these dense intersections, that the cosmic web reveals its true dynamic nature, not as a static sculpture, but as a living, breathing, and sometimes violent ecosystem. Between these brilliant galactic cities and their connecting highways lie the great cosmic deserts, regions of profound emptiness known as voids. These are the other half of the cosmic web's architecture, the immense negative space that gives the filaments and nodes their definition. A single void can stretch for hundreds of millions of light years, a volume of space so staggeringly large that our entire Milky Way galaxy would be just a tiny, insignificant speck within it. If you were to find yourself adrift in the heart of one of these voids, the universe would appear profoundly dark and lonely. The nearest major galaxy might be tens of millions of light years away, a faint, unreachable island in an ocean of black. This is not a place where stars are born. It is a place where the universe has, for the most part, simply given up. The gravitational pull of the surrounding web has relentlessly siphoned away the gas and dark matter that once resided here, leaving behind a cavern of near nothingness. Yet even these cosmic deserts are not perfectly empty. If you look closely, you might find a few isolated galaxies, solitary wanderers that were left behind when the rest of the matter was drawn out. These lone galaxies, often small and faint, tell a story of their own, having evolved in total isolation, untouched by the collisions and interactions that shape galaxies in the crowded clusters. Their quiet, uneventful lives provide a unique control group for astronomers, a way to understand how a galaxy develops when left entirely to its own devices. The existence and growth of these voids are more than just a curiosity. They are a powerful probe of the universe's most mysterious component, dark energy. As dark energy accelerates the universe's expansion, it also accelerates the growth of these voids, causing them to become larger and emptier over time. By meticulously measuring the sizes and shapes of voids, cosmologists can trace the influence of dark energy across cosmic history, using emptiness itself to understand the force that dominates our universe's fate. The Great Cosmic Web is a structure defined as much by its profound absences as by its glittering assemblies, a tapestry where the empty spaces are just as vital to the overall design as the threads themselves. But the filaments of the cosmic web are not woven from darkness alone. They are traced in ghostly light by a substance known as the Intergalactic Medium. This is the thin, primordial gas that fills the vast expanses between galaxies, a diffuse plasma of hydrogen and helium that is the true leftover ash from the Big Bang. After all the stars and galaxies formed, the overwhelming majority of the universe's ordinary matter did not end up inside them. Instead, it was spread out across these invisible threads, creating a cosmic atmosphere so thin that a single cubic meter of it might contain only a single atom. Yet, across billions of light years, this tenuous gas adds up to become the most massive visible component of the entire cosmic structure. We cannot photograph this gas directly, but we can detect its presence by using the universe's natural flashlights, quasars. These are the intensely bright cores of distant galaxies, powered by supermassive black holes. As the light from a quasar travels across the cosmos toward our telescopes, it passes through the filaments and voids of the intergalactic medium. The specific atoms in this gas absorb very particular colors from the quasar's brilliant white light. When we break that light into a rainbow-like spectrum, we see dark lines like missing pieces at those specific colors. Each of these absorption lines is a forensic mark, a signature that tells us exactly what element the light passed through and how much of it was there. By studying the light from thousands of quasars, astronomers can assemble a three-dimensional map of this invisible gas. The map reveals a universe laced with hydrogen, a confirmation that the cosmic web is real and that its filaments are filled with tangible, albeit incredibly thin, material. This intergalactic medium is the visible breath on the dark matter's mirror. It clings to the invisible gravitational skeleton, making the architecture of the cosmos visible to our instruments. It is densest within the great filaments, flowing along them like a faint cosmic wind, and it is thinnest within the profound emptiness of the voids. This distribution is not random. It is a perfect tracing of the underlying dark matter blueprint. The gas is caught in the same gravitational currents, pulled into the same rivers that guide the galaxies. And this is its crucial role. It is the primary fuel reserve for the entire universe. This gas is what flows along the cosmic highways, streaming into the waiting galaxy clusters and feeding the birth of new stars. Without this continuous replenishment from the intergalactic medium, galaxies would have consumed their original gas long ago, and star formation would have sputtered out across the cosmos. The Great Cosmic Web is not just a static map, it is a dynamic circulatory system, and this invisible gas is the lifeblood that sustains the glittering cities of galaxies. These frozen sound waves from the infancy of the cosmos provide a yardstick of almost unimaginable precision. They are known as Baryonic acoustic oscillations, a complex name for a beautifully simple concept. To understand them, we must travel back to a time before the first galaxies, even before the first atoms, when the universe was a seething, opaque plasma of particles and light. In this hot, dense soup, ordinary matter, which scientists call baryonic matter, was coupled tightly with radiation. Gravity tried to pull matter inward to form clumps, but the intense pressure of the light photons pushed it back out. This created a tug of war, a continuous cycle of collapse and rebound that sent powerful spherical pressure waves rippling outward through the plasma, much like sound waves moving through air. These were the very first sounds of the universe, a deep, resonant hum echoing through creation. Then, at the moment of recombination, when the universe cooled enough for atoms to form, the music suddenly stopped. The light decoupled from the matter and streamed freely across space, becoming the cosmic microwave background we detect today. The matter, suddenly freed from the relentless pressure of radiation, was left frozen in place. Each of those spherical sound waves was caught mid-ripple, leaving a distinct imprint in the distribution of matter. This created a preferred, standard distance between matter clumps, a cosmic fingerprint with a very specific size. That characteristic scale, the radius of that frozen sound wave, is about 500 million light-years. This is the universe's built-in ruler. When we look at the cosmic web today, we can still see this ancient echo. The distribution of galaxies is not completely random. There is a subtle but statistically undeniable preference for pairs of galaxies to be separated by this specific distance, the same 500 million light-year scale. It is as if the glitter sprinkled along the cosmic web's filaments has a preferred spacing, a rhythm set in stone during the universe's first 400,000 years. This makes baryonic acoustic oscillations one of the most powerful tools in all of cosmology. By measuring this standard ruler at different distances, and therefore at different epochs in cosmic history, astronomers can track how the scale of the ruler has been stretched by the expansion of the universe. It acts as a direct probe of dark energy, the mysterious force driving that acceleration. If the expansion were slowing down, the ruler would look one way as we measure it in the distant, early universe. But because the expansion is accelerating, the ruler's apparent stretching tells a different story, confirming the presence and influence of dark energy. This means the Great Cosmic Web is not just a structure, it is a historical record. Its very architecture, the precise spacing of its galaxies, encodes the history of the universe's expansion, offering us a direct link from the vibrant web we see today back to the first sounds of time. This relentless expansion is not just stretching space, it is actively reshaping the cosmic architecture. Dark energy, the mysterious force driving the acceleration, has become the dominant sculptor of our modern universe. Its influence is subtle but profound, acting like a cosmic counterweight to gravity's pull. Where gravity works tirelessly to pull matter together, weaving the web, dark energy works to push it apart, stretching the fabric of the cosmos itself. This grand cosmic tug-of-war is now tipping in dark energy's favor. We can see its signature in the growing emptiness between the threads. The great voids are not static, they are expanding. As the universe accelerates, these cosmic deserts are being stretched ever larger, their boundaries pushed outward by the invisible pressure of dark energy. The filaments of the web, those great cosmic highways, are themselves being pulled taut, becoming longer, thinner, and more tenuous over billions of years. The flow of gas along these rivers is slowing, as the increasing distances make it harder for gravity to pull material together. This leads us to a startling vision of the far future, a fate known as the Big Rip. If dark energy continues to strengthen, its influence could become so overwhelming that it would overcome every force that holds structures together. First, the cosmic web would be severed, with galaxy clusters becoming unbound and flying apart. Then, the gravitational pull within individual galaxies would be overcome, tearing stars from their orbits. In the final, terrifying moments, even planets, molecules, and atoms themselves would be ripped asunder by the accelerating expansion of space. While this ultimate fate is not certain, it highlights the incredible power of this mysterious force. Understanding dark energy's precise effect on the cosmic web is now one of the most urgent goals in all of science. By meticulously measuring how fast voids are growing and how filaments are stretching, cosmologists are using the web as a giant laboratory to probe the nature of dark energy itself. The ultimate fate of the universe's largest structure and everything within it hangs in the balance of this invisible cosmic struggle. This invisible architecture is not just a backdrop, it is an active construction site for the universe's visible content. Galaxies do not light up at random, they bloom along the luminous threads of the cosmic web, tracing its structure like dewdrops on a spider's silk. The reason is fundamental, a simple matter of cosmic real estate. The filaments of the web are where the raw material of creation, hydrogen gas, reaches a critical density. It is here that gravity can finally overcome the expansion of space, pulling vast clouds of gas together until they collapse under their own weight, igniting the first fires of stars and birthing new galaxies. Think of the cosmic web as a colossal, city-wide plumbing system. It gathers the sparse gas that lingers in the immense voids and funnels it efficiently into the dense pipes of the filaments. This gas then flows steadily along these cosmic conduits, its final destination being the brilliant, crowded intersections, the galaxy clusters. This continuous delivery of fresh fuel is what keeps the universe's stellar factories running, allowing new stars to form even billions of years after the first galaxies assembled. The type of galaxy that forms depends entirely on its address within this great cosmic network. Within the quiet, sprawling suburbs of the filaments themselves, you often find dwarf galaxies. These smaller collections of stars form from the gas that pools and condenses along the quieter stretches of the cosmic highways, away from the gravitational turmoil of the major intersections. But if a galaxy forms at a busy node where multiple filaments converge, its fate is dramatically different. It is born into a dense, chaotic metropolis, constantly bombarded by other galaxies and flooded with incoming gas. Here, galaxies can grow to immense sizes, often merging with their neighbors to become giant elliptical galaxies, their spiral structures erased by relentless collisions. This is why the cosmic web is so much more than a map. It is a master sculptor. The very geometry of the web, the local density and the direction of the gravitational flows imprints itself on every galaxy. A galaxy spinning within the steady current of a filament might retain its beautiful spiral arms, while a galaxy jostled in a dense cluster might be stripped of its gas, becoming a red and dead elliptical, its star-forming life cut short. By meticulously studying the properties and positions of millions of galaxies, astronomers can perform a kind of cosmic deduction. The patterns we see in the visible light, the distributions of spiral and elliptical galaxies, the rates of star formation, all of these are clues that point back to the invisible dark matter skeleton that supports them. This intricate relationship reveals a true cosmic ecology, a system where the flow of matter along an invisible framework directly dictates the growth, evolution, and ultimate fate of every glittering island in the sky. This grand cosmic architecture may even hold the key to one of the most pressing mysteries in modern cosmology, the Hubble tension. For years, astronomers have faced a stubborn discrepancy. When we measure the universe's current rate of expansion using nearby objects, we get one number, but when we calculate it based on the early universe's conditions, we get a slightly different, smaller number. They should match, but they do not. The question is, why? One compelling possibility is that the cosmic web itself is creating this illusion. Our entire local group of galaxies exists within a specific patch of this vast network. What if our neighborhood is not entirely average? Some cosmologists propose we reside in a local void, a region of the cosmic web that is slightly less dense than the universal average. Think of it like living in a gentle valley while the rest of the universe is on a high plateau. This underdensity would have a subtle but real gravitational effect. The slightly weaker pull from the surrounding matter could allow the space in our local region to expand a bit faster than the cosmos as a whole. When we measure the Hubble constant from within this cosmic valley, we would naturally get a slightly higher reading, precisely because our local space is stretching more rapidly. It is not that the entire universe is expanding at that faster rate, but that our local yardstick is skewed by the specific geometry of the web around us. This means the Hubble tension might not be an error in our physics, but a clue. It could be the first direct evidence that our place in the cosmic web is not typical, forcing us to account for the grand structure's local wrinkles when we take the universe's vital signs. Resolving this puzzle requires an even more detailed map of the web's geometry in our cosmic backyard, turning the largest structure in the universe into a precision tool for understanding its most fundamental behavior. The hidden gas of the cosmic web reveals itself in the most delicate of astronomical signatures, a phenomenon known as the Lyman alpha forest. When astronomers point their telescopes at a brilliant, distant quasar, they are not just seeing a single point of light. They are capturing a beam that has traversed billions of light years, passing through the countless threads and filaments of the intergalactic medium on its journey to us. As this light travels, clouds of neutral hydrogen gas, strung along the cosmic web like beads on a string, absorb very specific colors from the quasar's brilliant white light. The result is not a clean, simple spectrum, but a chaotic forest of dark absorption lines, each one a fingerprint left by a different hydrogen cloud at a different distance. Each line in this forest is a data point, a marker in space. By analyzing the precise pattern and density of these lines, astronomers can perform a kind of cosmic tomography. They can reconstruct the three-dimensional distribution of this primordial gas, revealing the fine, wispy tendrils of the web that are too faint for galaxies to illuminate. This is how we see the invisible rivers directly, mapping their flow and temperature with incredible precision. The Lyman Alpha Forest provides a resolution that galaxy surveys alone cannot match, showing us not just where the galaxies have gathered, but the intricate plumbing of the gaseous currents that feed them. It confirms that the cosmic web is not a theoretical sketch, but a physical, tangible structure woven from both dark matter and this faint, pervasive gas. This technique even lets us watch the web evolve. By observing quasars at different distances, we look back in time, seeing how the forest of absorption lines was denser and thicker in the early universe, when the web was first assembling, and how it has thinned and clarified over billions of years as the structure matured. The Lyman Alpha Forest is more than a measurement. It is the ghostly echo of the universe's circulatory system, a whisper from the vast, empty spaces that tells us the cosmos is alive with flowing rivers of creation. This hot gas reveals itself by casting a shadow on the oldest light in the universe. The phenomenon is called the Sunyaev-Zeldovich Effect, and it works like a cosmic silhouette. The cosmic microwave background radiation, that ancient glow from the infant universe, continues its journey across space. But when it passes through a massive galaxy cluster, it does not travel through empty space. It plunges through a seething ocean of incredibly hot gas, a plasma where electrons are so energetic they roam freely. As these ancient CMB photons fly through this hot cloud, they collide with these high-energy electrons. The collision gives the photons a tiny boost of energy, a kick that pushes them to slightly higher frequencies. This interaction leaves a distinct fingerprint, a specific distortion in the spectrum of the cosmic microwave background. From our perspective, it looks as though the cluster is casting a shadow, a small, cold spot against the warm background. This shadow is not a true absence of light, but a telltale sign that the light has been altered. The power of this effect is its incredible reach. Unlike optical telescopes that struggle to see the faintest, most distant clusters, the Sunyaev-Zeldovich effect allows us to find them regardless of how far away they are. The distortion is independent of distance, making it a perfect tool for taking a census of the universe's most massive structures. Satellite missions like Planck have scanned the entire sky using this technique, identifying thousands of galaxy clusters, many of which were previously unknown. They are not just mapping the clusters themselves, but also tracing the distribution of the incredibly hot gas that fills them. This gas is the atmosphere of the cosmic web's great cities, and its thermal energy is a direct record of the violent processes of cluster formation. By measuring the depth of these shadows, astronomers can calculate the pressure and density of this scorching plasma, understanding how much energy is stored within the nodes of the web. This is a crucial piece of the puzzle, revealing the energetic components of the cosmic architecture that are completely invisible to other forms of observation. These rivers of galaxies are not a gentle drift, but a powerful, directed current. Across the cosmos, entire clusters and superclusters are caught in these immense flows, moving at hundreds of kilometers per second as they are pulled by the gravitational might of the cosmic web. This is not the smooth, uniform expansion of the universe, but a specific, targeted motion toward the densest nodes in the network. To map these currents, astronomers must perform a kind of cosmic cartography, measuring not just where a galaxy is, but precisely how it is moving through the expanding fabric of space. By subtracting the general expansion, they reveal these peculiar velocities, the secret tributaries that trace the flow of matter on the grandest scales. These flows are the ultimate testament to the Webb's invisible gravity, a dynamic confirmation that the dark matter skeleton is not a static blueprint, but a living, pulling force that guides the destiny of everything we see. One of the most famous examples lies in our own cosmic backyard, a mysterious region we call the Great Attractor. For decades, we knew our Milky Way, along with our entire local group of galaxies, was moving at a staggering speed toward a point in the constellation Centaurus, pulled by something colossal we could not directly see. The Great Attractor is a massive gravitational anomaly, a huge knot in the cosmic web whose visible light is obscured by the dust of our own galaxy's disk. It is the combined pull of this hidden node and an even larger structure beyond it, the Shapley supercluster, that creates the powerful current we are riding. The Shapley supercluster is one of the most massive concentrations of matter in our observable universe, a gravitational beacon so potent it draws galaxies from hundreds of millions of light years away. Our local flow is just one small eddy in this vast cosmic river, all streaming toward the immense mass of Shapley. By meticulously tracing the direction and speed of these galactic rivers, astronomers can work backwards, using the motion of the water to map the shape of the hidden riverbed. The patterns of these cosmic flows allow scientists to reconstruct the detailed distribution of all mass, both visible and dark, throughout space. If galaxies are flowing toward a particular point, there must be an immense concentration of mass there, pulling them in. This technique turns the galaxies themselves into probes, their trajectories painting a dynamic picture of the underlying dark matter architecture. The agreement between these flow maps and the web predicted by supercomputer simulations is yet another powerful validation of our entire cosmological model. It proves that the cosmic web is not just a beautiful structure, but a functional gravitational engine, one whose relentless pull continues to shape the paths of galaxies billions of years after the first threads were spun. The Great Wall is not merely a cluster of galaxies, it is a continent of them, stretching for more than 500 million light-years. This vast sheet of galaxies was one of the first superstructures ever discovered, a landmark that forever changed our sense of cosmic scale. Imagine a single, flat wall of glittering cities so immense that light itself needs 500 million years to travel from one end to the other. This is not a solid barrier, of course, but a colossal filament of the cosmic web seen edge-on, a dense plane where the threads of the web have woven themselves together into a single, staggering sheet. Within this wall, thousands of individual galaxies are aligned, tracing out the underlying dark matter riverbed. Its discovery in the 1980s was a profound shock to the astronomical community. According to the prevailing theories of the time, such gigantic structures should not have had enough time to form given the age of the universe. The Great Wall stood as a direct challenge, a piece of observational evidence that forced cosmologists to rethink their models of how gravity assembles the cosmos. It was proof that the cosmic web could organize matter on scales that were almost incomprehensible, pushing the very limits of what we thought was possible. Later surveys revealed an even more colossal architecture, the Sloan Great Wall, a structure so vast it seemed to test the cosmological principle itself, the idea that the universe should look roughly the same in every direction. These titanic walls are the ultimate expression of the web's connectivity. They form at the intersections of multiple filaments, where the gravitational currents from different directions merge to create immense, flattened planes of matter. A wall is a web superstructure, a higher level of organization in the cosmic hierarchy. It shows us that the web is not a simple, uniform lattice. but a complex architecture with its own distinct features, from the delicate single threads to these monumental intersecting planes. By studying the Great Wall and its even larger cousins, astronomers gain crucial insights into the hierarchical nature of cosmic structure. They can measure how matter flows into these walls, how galaxies within them behave differently from those in isolated filaments, and how such immense structures eventually break apart under the relentless pull of dark energy. These cosmic continents are the endpoints of gravitational assembly, the final, majestic gatherings of matter before the great expansion begins to tear the web itself apart. These ghostly influencers are the universe's most elusive particles, neutrinos. Trillions of them are streaming through your body every second, yet they interact with matter so rarely that they pass through entire planets as if they were empty space. Born in the hearts of stars and in the cataclysmic violence of supernova, these nearly massless particles have been flooding the cosmos since its earliest moments. For a long time, we thought their minuscule mass meant they were merely cosmic spectators, having no real effect on the grand structures taking shape around them. But we are now learning that even the most ghostly of particles can leave a faint fingerprint on the architecture of the cosmic web. The key to their influence lies in their incredible speed and their refusal to be tied down. In the dense, early universe, dark matter and ordinary matter were slowed by their constant interactions, clumping together under gravity's pull. Neutrinos, however, behaved entirely differently. They free-streamed, racing away from the densest regions of the infant cosmos at speeds approaching light itself. This great neutrino exodus had a subtle but important consequence. As they fled, they carried a tiny amount of energy and momentum away with them, effectively robbing the densest knots of matter of some of their gravitational potential. This process gently suppressed the growth of the smallest cosmic structures. Think of a garden where you are trying to grow plants from seeds. The dark matter provides the rich soil. The ordinary matter is the water that helps the seeds grow. Neutrinos are like a persistent, very faint wind that constantly blows across the garden. It will not stop the largest trees from growing, but it can prevent the tiniest, most delicate seedlings from ever taking root. In the cosmic context, this means the very finest, most wispy tendrils of the cosmic web, the smallest dwarf galaxies and the thinnest gaseous filaments, may be slightly less abundant than they would have been without this ghostly wind. To create a truly accurate picture of the cosmic web, our most advanced supercomputer simulations must now account for this neutrino effect. When cosmologists include neutrinos in their virtual universes, they see a subtle shift in the resulting structure. The overall web looks the same, a magnificent network of filaments and nodes, but the statistical patterns change. There is a slight smoothing, a small but measurable reduction in the clumpiness of matter on the smallest scales. This alters how galaxies are predicted to cluster together. The precise statistical distribution of galaxies, the exact distances we expect to find between them, shifts in a way that matches our real observations only when neutrinos are part of the equation. While their individual impact is vanishingly small, the collective effect of countless trillions of neutrinos contributes to the total matter budget of the universe. They are a component of the dark universe we must now factor in. By studying the cosmic web in ever finer detail, we are essentially using the largest structure in existence as a delicate scale, one sensitive enough to weigh even the most ghostly of particles and confirm their subtle role in shaping everything we see. This invisible architecture is now being mapped with more than just light. We are entering the era of multi-messenger astronomy, a powerful new approach that uses different cosmic signals to build a single, unified picture of the universe. Think of it like trying to understand a vast, dark forest. If you only use your eyes, you see the shapes of the trees. But if you also listen to the sounds, feel the wind, and detect the scents on the air, the entire ecosystem suddenly comes to life in vivid detail. For cosmology, light from telescopes has been our only sense for centuries. Now we are learning to sense the cosmos in other ways. Gravitational waves are one of these new senses. These ripples in space-time, generated by colossal events like the merging of two black holes, carry information that light cannot. When we detect a gravitational wave signal, it pinpoints a violent cosmic merger. By identifying its location, we can often trace it back to a specific environment within the cosmic web, perhaps a dense node where such dramatic encounters are more common. This tells us not just that a merger happened, but where it happened within the grand architecture, revealing how the web's gravity influences the most extreme events. At the same time, the elusive neutrino offers another perspective. These ghostly particles, born in the hearts of stars and cataclysmic explosions, travel across the universe in near-perfect straight lines, unaffected by magnetic fields. A burst of neutrinos detected from a particular direction could act as a direct pointer, tracing a path back to an immensely dense region of the web, a hidden powerhouse that other signals might miss. The true power emerges when we combine all these messengers. A galaxy survey maps the visible structure. A gravitational wave event confirms a violent merger within a specific filament, and neutrino observations hint at the incredible energies being generated there. This integrated data creates a multidimensional map, showing not just where the mass of the web is, but how it is moving, shaking, and energizing the cosmos. This cross-validation is crucial. It tests our models of dark matter and dark energy in entirely new ways. If the distribution of gravitational wave events perfectly aligns with the nodes predicted by our dark matter simulations, it is a powerful confirmation that our blueprint is correct. The cosmic web is the ultimate backdrop for this multi-messenger symphony, the stage upon which all these different cosmic phenomena play out. By listening to the universe in every way we can, we are no longer just sketching its skeleton. We are feeling its pulse and beginning to understand the dynamic life flowing through its invisible veins. Could the largest structure in the universe have a subtle hand in the emergence of life itself? This vast cosmic architecture does more than just arrange galaxies. It actively curates the environments within them, creating conditions that are either ripe for life or profoundly hostile to it. The filaments of the web are the universe's most fertile regions. Here, the steady, gentle flow of gas provides a continuous supply of fuel for star formation. A higher rate of star birth naturally increases the probability that some of those stars will be stable, long-lived suns, and that around them, rocky planets will form within the habitable zone, that perfect orbital distance where liquid water can pool on a world's surface. These cosmic highways are the galactic equivalent of a temperate, resource-rich valley, offering a stable and sustained environment where life could potentially take root and evolve over billions of years. Yet at the crowded intersections of the web within the brilliant galaxy clusters, the story is dramatically different. These metropolitan hubs are crucibles of violence. The density of stars is so immense that planetary systems are frequently disrupted by close gravitational encounters, which could fling a fledgling Earth out into the cold, dark void of interstellar space. The space between galaxies in these clusters is also filled with intensely hot gas that emits powerful X-ray radiation, bathing entire star systems in sterilizing energy. Furthermore, the supermassive black holes at the centers of these galaxies are often active, unleashing jets of radiation that can scathe entire galaxies, effectively resetting the clock for any emerging biology. This creates a stark cosmic geography of life, a map of potential habitats and absolute deserts drawn by the invisible hand of the web. Our own Milky Way galaxy resides in a relatively quiet suburban filament, not too close to the chaotic urban center of a great cluster. This specific location may have been a crucial factor in allowing our solar system to develop in a stable, protected environment for long enough for complex life to arise. This leads to a profound and humbling thought. The cosmic web might not only be a structure of matter, but a framework for possibility, silently guiding the distribution of life across the immensity of the cosmos. The next generation of cosmic cartographers is already preparing to launch, armed with tools of unimaginable power, missions like the Euclid Space Telescope and the Vera-C. Rubin Observatory here on Earth are not just upgrades, they are a quantum leap in our ability to see the unseen. Their goal is nothing less than a complete, high-definition census of the cosmic web, mapping the positions and shapes of billions of galaxies across most of the observable universe. This is not merely adding more dots to the map, it is about revealing the texture of the canvas itself. One of their most powerful techniques relies on a subtle cosmic trick of the light, a phenomenon known as weak gravitational lensing. As light from distant galaxies travels across the cosmos toward us, it passes through the vast filaments and halos of dark matter that make up the web's skeleton. The gravity of this invisible mass acts like a lens, bending the light's path and very slightly distorting the shapes of those background galaxies. The effect is incredibly faint, like looking at a street lamp through the ripples of hot air rising from asphalt. Individually, each distorted galaxy tells us very little, but when you analyze the subtle, coherent warping across billions of galaxies, a pattern emerges. This collective distortion allows scientists to create a detailed mass map of the intervening dark matter, effectively taking a photograph of the invisible cosmic architecture. These future surveys will combine this lensing data with exquisitely precise measurements of galaxy clustering, using the Baryonic acoustic oscillations as a standard ruler to chart the expansion history of the universe with phenomenal accuracy. Every piece of data will be a cross-check against our current models of dark matter and dark energy. Does the web's growth over time match the predictions of our simulations? Does the way galaxies cluster together on the largest scales align with the blueprint from the cosmic microwave background? Any tiny but persistent deviation could be the clue that leads us to new physics, perhaps a deeper understanding of what dark energy truly is, or even a hint that dark matter has properties we have not yet dreamed of. The map these missions produce will be more than a static image. It will be a dynamic film of the universe's evolution, a storybook written in gravity and light. It promises to transform the cosmic web from a magnificent concept into a precisely measured reality, defining the fundamental structure of our cosmos for generations to come. This cosmic tapestry has been continuously rewoven since the very beginning. The web we observe today is just a single frame in a film spanning billions of years, a dynamic structure with a dramatic past and a startling future. In the universe's youth, the filaments were not the long, elegant rivers we see now. They were shorter, denser, and more numerous, like a tangled skein of yarn. Countless small threads crisscrossed the cosmos, and through a relentless process of gravitational merging, they combined. Smaller filaments were swallowed by larger ones, strengthening the main thoroughfares and leaving the faintest tendrils to fade away. At the same time, the great nodes were growing. Small galaxy groups, drawn together by these converging filaments, collided and merged to form the immense clusters we identify as the web's metropolitan hubs. This growth is mirrored by the voids, As matter was relentlessly siphoned out of these regions and into the growing web, the voids themselves expanded, becoming ever larger and emptier, their boundaries sharpening as the contrast between something and nothing intensified. You can see this progression clearly in supercomputer simulations, which act as time machines for the cosmos. They show the universe maturing, its structure clarifying over billions of years. The faint, blurry network of the early cosmos sharpens into the stark, intricate lacework of the modern universe. But this story of growth and assembly is now entering a new, final chapter. The future of the web is dictated by dark energy. As the cosmic expansion accelerates, the threads of the web will begin to stretch and fray. The flow of fresh gas along the filaments will slow to a trickle and then stop entirely, cutting off the galaxy clusters from their fuel supply. The great voids will continue to swell, pushing the filaments further apart and making them longer, thinner, and more tenuous. In the farthest future, dark energy's grip may become so powerful that it severs the cosmic web completely. Galaxy clusters will become unbound, drifting apart in an ever-cooling, ever-expanding emptiness. Individual galaxies will become isolated islands, their lights burning in a darkness so profound that no other galaxy will be visible in their skies. This grand structure, which took over 13 billion years to build, will be slowly taken apart. By studying this entire life cycle, from its quantum origins to its dark energy demise, cosmologists are reading a history book written in gravity and spacetime. The web's evolution is a direct record of cosmic time, a chronicle of how the universe grew up and what its ultimate fate will be. For decades, a cosmic accounting problem has puzzled scientists. We can calculate how much normal matter, the stuff of stars and planets and you and me, should have been created in the Big Bang. Yet when we add up all the visible matter in galaxies and clusters, more than half of it is simply missing. This is the mystery of the missing baryons, and the answer has been hiding in plain sight, woven into the fabric of the cosmic web. These lost atoms are not in some distant, unknown realm. They are floating in the immense, diffuse filaments that connect the galaxies, forming a cosmic atmosphere known as the warm, hot intergalactic medium. Imagine a fog so thin that a single coffee mug of it would contain fewer atoms than the best vacuum we can create on Earth. Yet spread across billions of light years of filament, this wispy gas adds up to the single largest reservoir of ordinary matter in the entire universe. The reason it has been so difficult to find is that it does not glow like a star. This gas is heated to temperatures of hundreds of thousands or even millions of degrees, not by fusion, but by the sheer violence of being funneled into the web's gravitational currents. At these temperatures, it does not emit visible light, only a faint whisper of X-ray radiation that is incredibly difficult to detect against the background of the cosmos. So how do we find something that is both incredibly hot and nearly invisible? Astronomers use the universe itself as a backlight. When the intense X-ray light from a distant quasar travels through one of these filaments, the superheated gas within the filament absorbs very specific colors from that light, leaving a telltale fingerprint in the quasar spectrum. It is like analyzing the light from a distant street lamp through a thick fog. The specific colors that are missing reveal the exact composition of the fog itself. Another method uses the same shadow casting technique we use on galaxy clusters, the Sunyaev-Zeldovich Effect. Even this diffuse gas is hot enough to give a tiny energy kick to the photons of the cosmic microwave background as they pass through, creating a minute but measurable distortion. Each of these detections is a small triumph, a few more atoms checked off the cosmic inventory sheet. Finding these missing baryons does more than just balance the books. It confirms that the cosmic web is the universe's primary storage system for its raw material. This warm, hot intergalactic medium is the ultimate source of fuel for galaxy growth, a vast reservoir that can slowly drip onto galaxies, sustaining star formation over billions of years. Without this hidden ocean of gas, our models of how galaxies form and evolve would be fundamentally incomplete. The Great Cosmic Web is not just an architectural marvel. It is the universe's warehouse, holding in its invisible threads the very stuff of creation that had, until now, been lost to our sight. The invisible threads of the cosmic web may be woven from the fabric of spacetime itself. This grand architecture could be our most powerful link to a theory of everything, a bridge between the universe of the very large and the realm of the infinitesimally small. For decades, physicists have sought to unite Einstein's theory of general relativity, which governs gravity and the cosmos, with quantum mechanics, the rules of the subatomic world. These two pillars of modern physics are fundamentally at odds, and finding a single framework that describes both has been the ultimate goal. The cosmic web offers a unique testing ground. Its initial seeds, those tiny ripples stretched by inflation, were born from quantum fluctuations. This means the largest structure we can observe was fundamentally sculpted by quantum processes. The specific statistical patterns in the web's arrangement, the precise way galaxies cluster and voids form, could potentially hold faint imprints of those first quantum moments. It is like analyzing the intricate pattern of a snowflake to understand the molecular properties of water, only on a cosmic scale. Some speculative theories of quantum gravity predict subtle deviations in these patterns, tiny statistical anomalies that would not exist in a purely classical universe. Finding such a signature would be monumental. It would mean that by mapping the distribution of galaxies across billions of light years, we are indirectly reading the quantum script written at the birth of time. This turns the entire cosmic web into a natural particle accelerator, but one of unimaginable scale. We do not need to build a collider larger than a solar system. The universe has already provided one. By meticulously measuring the cosmic web's geometry and comparing it to predictions from different theories of quantum gravity, we can perform experiments that are otherwise impossible in any laboratory on Earth. While this connection remains a thrilling frontier, it underscores a profound truth. The Great Cosmic Web is more than a structure of galaxies. It is a historical document, a cosmic fossil, and perhaps our best hope for glimpsing the unified laws that orchestrate all of reality. This grand design has reached far beyond the pages of scientific journals to spark a fire in the human spirit. The cosmic web resonates with something deep within us, a profound sense that the universe is not a chaotic scattering of lights but a unified, interconnected whole. You can see its influence blossoming in modern art, where digital renderings of the web's delicate filaments have become a new form of cosmic landscape painting, translating vast data sets into breathtaking visual symphonies. These are not just illustrations, they are portals, allowing us to step inside the invisible architecture and feel its scale. In literature and film, the metaphor of the web has become a powerful narrative device, representing everything from the hidden networks of fate to the intricate bonds that connect all conscious life across the stars. This is more than just borrowing a scientific term. It is a reflection of a fundamental shift in our cosmic perspective. For centuries, we saw ourselves as inhabitants of a lonely island, adrift in a silent, empty ocean. Now, the image of the web tells a different story, one of intrinsic connection. It suggests that our galaxy, our sun, our world, is a single thread woven into a tapestry of unimaginable grandeur. This vision directly challenges the ancient fear of cosmic isolation, replacing it with a humbling yet comforting sense of belonging to something vast and beautifully structured. The cultural power of the cosmic web lies in this dual ability to awe and to unite. It makes the abstract tangible, transforming cold data into a story that speaks to our innate desire to find patterns and meaning in the cosmos. By becoming a cultural icon, the web does not just communicate science, it inspires a new generation to look up at the night sky and see not just points of light, but the glittering nodes of a single, magnificent creation. You can now reach out and touch the architecture of the universe. Interactive simulations and stunning visualizations have transformed this abstract cosmic concept into something you can explore with your own hands. Programs like Universe Sandbox put the power of creation at your fingertips, allowing you to witness firsthand how a smooth cloud of virtual particles collapses under its own gravity, weaving itself into a delicate web of filaments and nodes. These are not just animations, they are dynamic playgrounds governed by the real laws of physics, where you can experiment with dark matter's pull and watch as galaxy clusters form at the intersections of invisible rivers. In planetariums around the world, these digital models are projected across vast domes, immersing audiences in a flight through the cosmic web. You do not just learn about the structure, you feel its scale, sailing past glittering galactic cities connected by long, luminous threads. This immersive experience makes the immense distances and grand processes tangible, translating billions of light years into a comprehensible and awe-inspiring journey. Educational programs are harnessing these powerful tools to teach the fundamentals of cosmology. Students are no longer passive recipients of facts, they become active participants in the universe's evolution. They can adjust the amount of dark matter in a simulation and watch as the web grows spindly or robust, or rewind time to see how the great walls of galaxies assembled from tiny quantum seeds. This hands-on engagement demystifies complex ideas, allowing a child to intuitively grasp how gravity, acting over eons, can sculpt the largest structure in existence. By democratizing this knowledge, we are not just sharing information, we are inspiring a sense of ownership and wonder. A student manipulating a virtual cosmos today might be the cosmologist who solves the mystery of dark energy tomorrow. These tools build a bridge connecting the human scale of a classroom or a laptop screen directly to the grand, invisible tapestry that binds the entire cosmos. The vastness of the cosmic web does not diminish our significance but reframes it. This grand architecture offers a profound lesson in perspective, one that echoes with urgent ethical implications for our time. When we truly grasp that we are a thread within this universal tapestry, our countless earthly conflicts and borders begin to seem like fleeting, inconsequential details. The cosmic web presents a humbling vision, forcing us to confront our own smallness not with despair, but with a deep sense of shared destiny. We are all, regardless of nationality or creed, inhabitants of a single, fragile world, riding together on a speck of dust adrift in an ocean of invisible filaments. This realization can be the very catalyst for a new kind of global cooperation. The challenges of space exploration, from establishing a sustainable presence on the Moon to one day venturing toward Mars, demand international collaboration on a scale we have never before achieved. They require us to pool our knowledge, resources, and ingenuity, not as competing nations, but as a unified species taking its first steps into the cosmic neighborhood. This perspective directly informs our most pressing planetary responsibility, environmental stewardship, seeing Earth from this cosmic vantage point as a solitary, brilliant blue and white marble set against the immense blackness, underscores its absolute uniqueness and fragility. The atmosphere that protects us, the oceans that sustain us, they are unimaginably thin layers, the only home we have ever known. Protecting this delicate biosphere is no longer just an environmental goal, it is a fundamental duty of our cosmic citizenship. To allow this singular world to be degraded is to fail in our most basic responsibility to the future. The cosmic web, therefore, calls us to a higher purpose. It encourages a perspective that values curiosity and knowledge for their own sake, that sees the preservation of our planet and the peaceful exploration of space as two sides of the same coin. It asks us to consider what legacy we wish to leave, not just for the next generation, but for any future consciousness that might one day look back and see our tiny, interconnected world as a shining example of wisdom and hope in a vast, interconnected cosmos. The cosmic web sings. Scientists have discovered a way to hear its architecture by translating the immense data of galaxy surveys into sound, a process called sonification. They assign specific musical pitches to the density of matter. Where the dark matter filaments are thickest and galaxies crowd together, the notes rise into clusters of higher pitch, creating intricate, interwoven melodies. In the vast, empty cosmic voids, the sound drops away into profound and extended silences. This auditory map is more than a beautiful symphony. It is a powerful analytical tool. The human ear is exceptionally good at detecting subtle rhythmic patterns and shifts in tone that the eye might miss in a complex visual graph. By listening to the data, researchers can sometimes identify faint substructures or unusual alignments within the web's filaments that were not immediately obvious. This innovative approach also shatters barriers, making the grandest structure in the universe accessible to visually impaired astronomers and enthusiasts, allowing them to experience the cosmos's scale and complexity through a different sense. The rhythmic cadence that emerges from the data reveals a hidden musicality within the cosmic architecture, a harmony born from gravity's slow, patient work. This creative fusion of science and art reminds us that the universe is a multidimensional experience, and that its deepest secrets can be uncovered not just by looking, but by listening to the silent music of the spheres. This cosmic tapestry is not a frozen sculpture. It is a living, breathing entity with a history, a present, and a future. We are not seeing the web as it is, but as it was. Light from the most distant galaxies has traveled for billions of years to reach our telescopes. When we observe a filament 10 billion light-years away, we are peering directly into the cosmic past, witnessing the web in its raw, formative youth. In these ancient views, the structure appears more chaotic, a dense tangle of nascent threads just beginning to draw matter together. Compare this to the elegant, well-defined lattice of the nearby universe, and you witness a billion-year story of gravitational refinement. This ability to look back in time is the foundation of a new field, time-domain astronomy, which seeks to track the web's changes not over eons, but sometimes within a human lifetime. By repeatedly mapping the same vast volumes of space, astronomers hope to catch the web in the act of transformation. They could witness the slow, stately merger of two great filaments, a cosmic confluence that would funnel thousands of galaxies into a new, larger river. They might measure the imperceptible but relentless growth of a cosmic void as dark energy stretches its boundaries, making it emptier by the day. These are not sudden events, but the glacial tides of cosmic evolution. Capturing them requires immense patience and precision, but the reward is a dynamic movie of the universe's largest structure, rather than a single snapshot. This four-dimensional view, weaving time into the fabric of space, is essential for unlocking the web's complete story. It allows us to test our simulations not just against a final state, but against the entire process of growth. Does the web mature at the rate we predict? Do filaments merge in the way our models suggest? Each answered question tightens our grasp on the forces of dark matter and dark energy. To see the web in time is to understand it not as a thing, but as a story still being written, a chronicle of gravity's patient work and the counterforce that will one day unravel it all. Our own Milky Way galaxy is not a solitary wanderer, but a resident of a specific cosmic neighborhood. We are embedded within a great filament of the cosmic web, a structure so immense it has been given a name, the Laniakea supercluster. Laniakea means immense heaven in Hawaiian, a fitting title for a home territory that spans over 500 million light-years and contains more than 100,000 galaxies. Our local filament is a vast river of galaxies, and we are sailing within its currents. This is not an abstract concept, it is our cosmic address. The gravitational pull of this entire local web dictates our galaxy's motion. Our journey toward the Great Attractor and the even more massive Shapley supercluster beyond it is simply our path along this immense, invisible riverbed. The environment within our filament is relatively quiet, a galactic suburb that has allowed the Milky Way to evolve in a stable manner for billions of years, a likely prerequisite for our own existence. This local perspective is crucial for science. By studying the cosmic web right in our own backyard, we can calibrate our models and understand the detailed physics of galactic evolution up close. Projects like the Cosmic Flows Survey are dedicated to this exact task, meticulously measuring the distances and velocities of thousands of nearby galaxies to create a high-resolution, three-dimensional map of our immediate surroundings. This map reveals the subtle gravitational currents, the smaller tributaries that feed into the major filaments, and the boundaries of our local void. It shows us with stunning clarity exactly how we fit into the larger network. The local web provides a unique close-up view of the universal processes of accretion and flow that shape all galaxies. It transforms the grand cosmic architecture from a distant marvel into a personal reality, a structure we are not just observing, but one we are actively a part of, living out our lives within its silent, gravitational embrace. This cosmic web stands as the ultimate testament to the universe's hidden grandeur. It is an invisible network connecting every galaxy across space and time, a structure so vast it defines reality itself. From the ghostly scaffolding of dark matter to the silent rivers of gas flowing along its filaments, we have journeyed through the forces that build and sustain this magnificent architecture. To understand this web is to unlock a deeper knowledge of the cosmos and our own small, yet significant, place within it. Future missions will soon map its entirety in stunning high definition, and with every new detail, fresh mysteries will certainly emerge to challenge our perception of reality. This entire exploration leads to one humbling truth. We are all, every one of us, part of this incredible cosmic tapestry, woven into its story from the very first moments of time. What does this vast interconnection inspire in you? Share your thoughts in the comments below. If these journeys into space's greatest mysteries captivate you, subscribe to keep exploring. And tonight, when you look up at the star-filled sky, remember you are not looking at isolated points of light, but at the glittering nodes of a single, connected universe.